We'll get going. Thanks everybody for coming. Today we have Dr. Phil Metzger. Phil has a BS and double E from Auburn and a PhD in physics from UCF, University of Central Florida. He spent 30 years at KSC providing engineering support. Is that
no? It was like half of that was as an engineer on the shuttle, and then half of it was as a physicist doing research and tech development.
And he was the co-founder of the SwampWorks, which was a fast development group at KSC. He was recognized for his contributions by NASA with a number of awards, including the Scientist Engineer of the Year, and also a Silver Snoopy Award, which is given by the Astronaut Corps for support for human spaceflight. And he was also the NASA Innovative Advanced Concepts Fellow. He's also director. Today, he's currently a research faculty at the University of Central Florida, and he's also director of the Stephen Hawking Center for Microgravity Research and Education. Phil is also going to be giving a lunch talk tomorrow focused on some of the geopolitical consequences of lunar exploration and some of the things he's going to be talking about in his science talk today. So welcome, Phil, and I'll let you take it away.
All right, thank you. Is the microphone working? Can you all hear me? Okay, good. Yeah, so I'm going to talk about plume surface interactions in lunar and Mars landings, mostly lunar, but I'll talk a bit about Mars. And tomorrow will be the implications, like how do we mitigate it, and geopolitical implications. Okay, so first off, plume effects are different in different environments. On the Earth and on Mars, the atmospheres are adequate to collimate the plume so that they are actually jets, and that constrains the pressure to a very small area with sharp boundaries, which causes shearing in the soil, which digs deep holes. On the moon, we don't have much of an atmosphere. In fact, this simulation was using more atmosphere than the moon has. But as a result, the plume spreads out very broadly, and you get a very large bowl-shaped shock wave. But most importantly, the pressure gradient along the soil, it's a low gradient. And so it's like using snowshoes to walk. It spreads the forces out so it doesn't cause shearing in the soil, and you don't get a deep crater formation, which causes people to say it was a hoax. We didn't really land on the moon because there was no crater. But we know why there was no crater. There actually was a crater, and I'll show you. But it was a toroidal crater. Okay, now there's been a lot of research on how rock exhaust or how wind blows soil here on the Earth, but that research is not really that relevant. I did a review of the literature again just a couple of years ago, and the study, when they try to study what is the rate that soil is moved as a function of wind properties, turns out saltation is the primary way that energy is transported to the surface. Sand grains pop up, they get accelerated in the higher velocity wind higher above the surface, and then fall back down, bringing the energy with them. And without saltation, what is the vector of energy to the surface? On the moon, the rocket exhaust exceeds lunar escape velocity, and so particles travel for kilometers, but the gas is spreading out radially, and so erosion only happens over a limited area. And so the first bounce of saltation takes it outside of the gas, and so there's no transport of energy from the gas to the soil by saltation. So what actually drives the erosion rate in the lunar case? And over the years of doing research, the research community has discovered there's actually a lot of different regimes of behavior. And on the moon, it's mainly surface scour. But I'm going to go through a few of these regimes. Some of these will occur on Mars, but they don't occur on the moon. The first thing we notice is looking down from space, there's an area where the soil gets brightened. Ryan Clegg Watkins was a student who interned with me a couple of summers. She's now at NASA headquarters, but she did her PhD research on this with Brad Jolliffe. And they measured and quantified the surface brightening. However, although it's very well quantified, we don't really know what causes it. Why is the radius of brightening 100 meters? Why isn't it a kilometer? Why isn't it 10 meters? We don't know what physics causes that. A second effect is shock impingement. When you ignite a rocket exhaust, the shock wave leaves the engine and goes down and hits the ground. And this is a funny story. I did this test at NASA. We were trying to prove that we could stop soil erosion by putting a layer of gravel on top of the soil. So I did the calculations and I proved what size gravel was required. I had to go out of town, and so they did the test when I was out of town. But meanwhile, a tour group came of all these VIPs, and they took the VIPs out to watch my test. Well, I forgot to take into account the shock impingement, which is about 10 times higher force than the steady state. And so this is what happened. It ignited. This is a high-speed camera slowing it way down. There's a gigantic splash of gravel. The gravel started hitting the audience like from the knee down. And everybody was making these jokes like, wow, these guys are really good at their safety barriers. They actually calculated it so it only hit us up to the knee. That was a big fail for me. But so shock splash. Another thing is surface scour, where you have this flow of gas over the surface, and by some mechanism it pushes grains, maybe it lifts grains, maybe there's turbulence, maybe there's diffusion into the soil that loosens it, moves it along as a rolling layer on the soil. There's various ways this could occur, but those are all surface behaviors. Now, the thing on the moon that makes it even more complicated is that the rocket exhaust is blowing into vacuum, and we don't even have computer models that can actually model the gas flow correctly. So in this simulation, we used two different computer models. We used Navier-Stokes equation, the CFD, to model close to the rocket nozzle. But after the gas expands into vacuum, it no longer obeys the Navier-Stokes equations. And so you use direct simulation Monte Carlo to monitor outside there. But the problem is, when the rocket exhaust hits the lunar surface, it gets a high dense region right here. And in this region, it doesn't, the DSMC model is not accurate. We should switch back to Navier-Stokes, but we can't, because DSMC is noisy and Navier-Stokes is unstable. And so there aren't really any computer models that can handle it well. And then when you mix in the soil behavior, it's even more complicated. So we've spent many years at NASA writing contracts to companies to improve the modeling. We've made a lot of progress, but we still can't model all the physics. Now, we know what happens is the sand grains in erosion scour get lifted. Now, this is a side view. The rocket nozzle is here, and this is the gas velocity. The gas is going slow under the nozzle. It speeds up and goes supersonic. But on the top view is the gas density. You can also see as you move out, it goes lower and lower density. And so there's a region of maximum erosion where the gas is fast and the density is still high enough that you get erosion. And so you get a toroidal crater that forms around. And the problem we have in the modeling is trying to predict how fast the particles get lifted into the faster gas flow. Modeling in this extreme environment is not accurate. And so all the different computer models predict the particles going velocities where the different researchers disagree with each other by a factor of 10. And we don't know who's correct. So we don't know within a factor of 10 the velocity of the ejecta on lunar landings. And there's no way to measure it yet either. We've never put an instrument on the moon that's able to measure the velocity of the ejecta directly. So as I mentioned, you'll get a toroidal crater that will form. Now here's another regime. This is diffused gas eruption. This was known back in the 1960s. What happens is you get that high pressure on top of the soil, and that drives gas into the soil through the pore spaces, through the permeability of the soil. But because the propagation or the transport of gas up here is different than down here, you get a pressure imbalance. And that pressure imbalance can actually eject soil. And then once it's ejected, it gets into the gas flow and gets blown away. But then also when you shut off your rocket engine, now you have a different imbalance, and that causes the gas to blow back up the center line. So that was hypothesized back in the 1960s, and it does happen. Another thing that was known since the 1960s is that sometimes that jet of gas can act like a mechanical penetrator and just shove the soil down, sort of like a cone penetrometer. And this has been broadly studied. we know that when a penetrator pushes into the soil pushes down, out, and then up. And so it causes this very large global movement of the soil in response to the penetrator. And because you're having to move so much soil, it's a lot of resistance. That's why if you try to shove a broomstick into sand, it's very hard to get it go down more than a couple of inches, because you're moving this giant volume of sand in response to the broom. And so it does sometimes happen. This is a test we did with a small rocket motor into a deep sand bed. Watch these layers of colored sand. You can see them getting pushed down as the crater grows. This is slowed way down with a high-speed camera. So you see it's shoving those layers down, and as it dug the hole. And it was a very clean hole. There was no sand being lifted out. It was just simply shoving down through bearing capacity failure. So that sometimes happens. But we did other tests where we put layers of colored sand in a sandbox, and we fired the jet, and we, after the test was done, we topped it off with black sand for contrast, filled it with clear epoxy, and then cured it and cut it in half to see how the sand moved. And what we discovered is, first of all, there's this slumping that occurred along shear planes. There's this deposit of material up at the top. This is where the ejecta blew up and then fell back down. So you can see the white layer zigzagging around. But the funniest thing is that the flow direction was like this. The sand was flowing up the center, like going against the direction of the gas jet. We didn't know how that could possibly be true. How can the gas blow down, but the sand goes up the center? Well, it turns out it was going up the center coaxially around the gas jet. And then when the gas jet shut off, the crater collapsed and it left it looking like this. But this is the opposite direction of flow of bearing capacity failure. Bearing capacity failure shoves sand down. This was bringing sand up. And so we started doing experiments against glass windows. Here's a crater outlined in red, and then we did tracking of individual sand particles, and we can see that there's a thick band of sand around the crater moving upward, and that's because the gas is diffusing into the crater, traveling a short distance, and then up near the top, the gas is exiting into the crater and carrying the sand away with it. So it's dragging the sand upward around the sides of the crater. And as long as the crater is short enough that the jet hits the bottom of the crater, then you get high pressure gradients and high forces in the sand. But once the crater grows deep enough that you get a constant pressure in the bottom, then you don't have much pressure gradient to drive the gas in that pattern. And so the forces become very small and the crater stops growing. And so this was a new regime we discovered. We called a diffused gas, diffusion-driven flow of the sand. And you either get bearing capacity failure or diffusion-driven flow, depending on the permeability of the soil. So different types of behaviors can occur in different conditions. One last one I'll mention is when you have an earthquake, the soil can fluidize and buildings can sink. That can happen with rockets too. A lot of times, to save money on rocket development, they will use an off-the-shelf motor which has too much thrust. And so they'll use pulse control, pulse width modulating the rocket engine to lower the average thrust. This is very common on planetary landers. And so you'll end up firing that rocket 10 times per second. And so you're slapping the soil at 10 hertz with shock waves, which is vibrating the soil and fluidizes the soil. And this is what happened on the Phoenix lander. It fluidized the soil and it very easily blew all the soil off, which exposed the ice. JPL did a lot of research, and University of Michigan did a lot of research to prove that that's what happened. So there's a lot of different ways that rocket exhaust can interact with soil. And some of those will happen on Mars with larger landers. Some of those did happen with Skycrane. And if you come tomorrow, I'll show more about that. Okay, so I'm going to focus now on the surface erosion, which was the dominant mechanism on the moon. In the Apollo landings, they had this data acquisition camera looking out the pilot side window of the lunar module. And this is an example. I think this was Apollo 15. What you'll see as they're descending to the moon, it'll start to get hazy in the lower corner. They're starting to get hazy. You'll start to see streaks forming. These are streaks that form around craters and rocks. You'll start to see the shadow of the lunar module footpad at the top, and that diagonal coming off of it is the soil contact probe. Then it's going to briefly stop blowing soil, and then a big burst and opaque chunks blew through the field of view. And then it takes about 20 seconds for the haziness to clear. There were a lot of things in there we didn't understand. I'm going to go through a little bit more detail here. So the smooth flow stage, where you're blowing this sheet of dust, then you start to get streak development. That's when the vehicle is getting lower. The shock wave is closer to the surface, which is causing more shear stress around the rocks and craters. And so you start to get streaks forming. That big blast that you see at the end is when it's blowing out bulk quantities of soil. I'll show you a little bit more about that in a second. We did identify rocks blowing in the videos, and we were able to measure the velocity of the rocks frame by frame. There had been a legend in Apollo that they didn't blow any rocks. Totally untrue. They just didn't look at the video close enough. These rocks are like 10 centimeters in diameter, blowing about, if I recall correctly, like 20 miles per hour or something like that. There's also these things that we call dust tails. We didn't know what they were. They would appear on the ground. They would only persist for 1 or 2 camera frames. If they were there for multiple camera frames, they wouldn't move. They would stay fixed, and then they would disappear. And we've later on figured out what it is, and I'll show you in a moment. This is that blast of soil. We could identify dirt clods that were blowing. They were like little comets because there was a nucleus that was slowly blowing away, and then there was a tail of fine material blowing off of that nucleus at a higher velocity. So that's how we knew they were dirt clods. They were friable material blowing with a lot of inertia, but shedding fine particles that had low inertia that would blow away faster. And because they were dirt clods, we knew that it had blown out bulk quantities of soil rather than just surface erosion. So this is what it looked like under Apollo 11. You can see a lot of effects. You can see all of these radial erosional remnants. Some of them are aligning behind little pieces of gravel that were still embedded in the soil. There was these cracks in the soil. I'm going to go back. You can see these cracks. Well, I think it's partly cutting off. Anyways, you can see enough of it. There's these cracks. They thought that those were cracks where a gas had diffused into the soil and then came back out again. But we later on proved that it was not really that. Up at letter A, there's a rock that's embedded in the soil with a protected tail of soil behind it. That's an erosional remnant. Down here at B, there's all these little bright line segments. These are little stair steps in the soil, stepping downhill away from the nozzle, little abrupt stair steps. Here you've got, is there a laser pointer? Yeah, you've got smooth soil up here, but it's real cobbly down here with a sharp edge contact between the two terrains. So we needed to explain that. Also, there's, oops, darn it. A lot of other erosional remnants here that are unheaded erosional remnants, but just little blobs that are aligned with the direction of gas flow. Okay, so we tried to explain all the phenomena by doing field testing. We took a thruster up onto Mauna Kea with high-speed camera, and we did a whole bunch of thruster firings on the volcanic tephra to see if we could get insight into these features. And so we, playing around, made little mini moonscapes with craters and boulders. It's kind of embarrassing now, but it was kind of fun at the time. And then we did a whole lot of tests, and we looked at the features of dust rings and arcs and streaks of the dust, and we decomposed everything in great detail. We were able to figure out what these dust tails were. Whenever the soil would start to would be eroding and it would start to expose a rock, then the rock would be sticking up in the gas flow, and the increased shear stress of the gas around the rock would cause enhanced erosion around the rock. And because you have enhanced erosion, you're liberating more dust in that area, which would form a dust tail. And because the rock is still half buried, it stays fixed in location. But as soon as you've dug around the rock enough that the rock can come up out of the hole and blow away, then you've taken away that obstacle to the wind, and so the dust tail disappears. And so we realized that those dust tails on the moon were actually rocks being exposed, and it gives us a very crude estimate of the rate that the soil is being lowered around the vehicle. Also, in these tests, we replicated from orbit on the moon. You see the brightening around landing sites. We saw brightening. Every time we fired a rocket exhaust in the soil would be brighter. The brightness was not a chemical change in the soil. The brightness was actually very, very fine dust And every time you fire the rocket, after you shut the rocket off, there would be this thin veneer of concentrated fine dust left on the surface, which was crazy, because why wouldn't rocket exhaust blow the dust away? How could the dust settle in the middle of a rocket exhaust and build up and concentrate on the surface in the middle of a rocket exhaust? This became an important clue later. But so I did a lot of work trying to understand this brightening. Oh, and you could go up to the ground and just kick the ground near the bright spot, and the vibration would make all the dust lift off and blow away. So the slightest mechanical disturbance, it would all leave. It's like, well, if kicking the ground makes it all leave, why didn't a rocket exhaust make it all leave? Big mystery at the time. But we studied these, the direction of airflow is shown by the arrows, and it would have scour pools around rocks that are dark, and then the right adjacent to it would be areas that are bright. And so we came to the conclusion that soil was eroding and becoming darker, but right next door, it was redepositing dust, making it brighter. So there was dust deposition going on at the same time that erosion was happening down in the fine details of the texture of the soil. Another shocking thing was we discovered the rocket exhaust would dig these craters that had stair steps. And so we did a lot of analysis to figure out why does the rocket dig a stair step? So the rocket exhaust was impinging the ground right about here. That's the deepest spot. And then it's stair steps going uphill away from that deepest spot. And so it was like an architect's model with terraces. Each terrace would be one level piece of ground, and it was terrace after terrace. So there were natural laminations in the soil. And after doing a lot of looking at it, we figured out that these terraces were alternating fine and coarse material. And so these were natural laminations in the tephra, probably caused by seasonal effects, the wind blowing, causing separation of fines and coarse, and then the wet season locking it down, and then another season, bringing more down into the valley and separating it again. So over time, you get these natural laminations of coarse and fine. With a little bit of moisture in the soil, the fines became very cohesive, and so the fines resisted erosion better. And so every time it was digging a crater down to a fine layer, it would meet mechanical resistance, and so you would get a stair step at the fine layers. Sometimes the coarse layers were completely removed, and sometimes there would be a lot of cobbly material left over where it had not been completely removed between the two fine layers. And so this led us to go back and reassess what we saw in these videos. Turns out these are not really fissures in the soil. These are stair steps. It's stepping downhill away from the rocket nozzle because erosion rate is faster farther away, which is the opposite of the terrestrial case. In the terrestrial case, it's deepest under the nozzle, and it goes uphill as you go away. In the lunar case, because the erosion rate is higher out here, you're going downhill as you go away. And so all of these little stair steps are like little natural laminations in the soil that were exposed by the erosion process. So apparently, there must be natural laminations in lunar soil with mechanical difficulties. And the height of that stair step is about 1 centimeter, which corresponds to the average, or about the average thickness of the impact ejecta blanket. So I think these are different impact ejecta blankets, but the funny thing is the mechanical discontinuity between them. Again, looking at this picture, now we can explain this. There's cobbly material out here. There's a contact, that's the stair step, and the smooth material, because this area, the layers above it were almost completely removed. There's still a little bit of cobbly material there, but the layer was almost completely removed, whereas the next layer down that's being removed hasn't been removed completely, so there's still a lot of coarse material sitting there.
So can I ask a question?
Yes.
Would you then infer that there's some moisture?
No, it's not moisture. The cohesion is, I can only speculate. I published this in 2011. It was in a paper on plume surface interactions. And because not a lot of people read those papers, unfortunately, it didn't get much attention. But I would really love if people would look into this and try to figure out the cause of it. Here's my speculation. I think that when an impact ejecta blanket lies on the surface, subjected to space weathering, the weathering is primarily in the top millimeter, causing the soil to be finer and more jagged, more glassy in that top millimeter. And the cohesion in lunar soil is it's more significant than on the Earth because lower gravity. So cohesion is already more dominant as a control on the behavior of the soil. But then when you get this enhancing of fines due to the space weathering, I think you get this millimeter layer between impact ejecta blankets. The funny thing, though, is when you get another impact ejecta blanket lying down on top of the earlier one, why didn't the deposition process cause more mixing? Why didn't it destroy those layers? I don't know. All I know is that we're seeing layers, and it's like every Apollo mission where we had good images, we find them. So here's another consistent long-range stair step in the soil, stepping downhill as you move away from the nozzle. Here's another one. There's some layers in here, some stair steps. So anyways, that's all I can say about it. It was an interesting thing that we noted, which I hope somebody will investigate. The next thing I want to move on to is trying to predict what happens to the ejecta after it gets lifted off the surface. We did a lot of analysis of the shadows of the lunar module foot pads. The shadows are elongated, and so we made physical models where we put a glass sheet and we put smoke under the glass sheet, and then a solar simulator, and measured the elongation of the shadows as the shadows are passing through the dust. And we did computer modeling of it, and then we worked the geometry, and we went out to the lunar module and we actually measured the geometry. And from the elongation of the shadows, we were able to calculate on 4 of the 6 landings that the ejection angle was between 1 and 3 degrees. Apollo 12, we couldn't measure it because the sun was so low on the horizon. The shadows were longer than the field of view of the camera, so we couldn't measure the shadows. So that one wasn't measurable. Apollo 15 was an outlier, but we understand why it was an outlier. When Apollo 15 was landing, they were moving forward as they were descending, and it turns out they were going over a broad, shallow crater. They couldn't see it because the dust covered it up. They landed on the far rim, and after they shut the engine off, the vehicle rocked back 12 degrees. And when the footpad hit the ground, one of the astronauts said, "Bam!" And because it surprised them that they rocked back and hit the ground. And so we were actually measuring the shadow of the dust is coming up at this angle, and we have this extra angle on the below the terrain outside the crater. So we understand it. So we did a lot of computer modeling, and the computer modeling was able to replicate 1 to 3 degrees. So the ejecta cone coming out of the rocket exhaust has an ejecta angle of 1 to 3 degrees in general. So the big question, though, was how much ejecta is being blown, because this determines how much of an impact it's going to have in the surrounding area. So we did a lot of experiments, the ones on the volcano, ones in our lab. We did reduced gravity flights. We went to NASA Ames, their big vacuum chamber, and did a lot of experiments. We fired hot rocket nozzles. This type of test was extremely useful because although it's small scale, you get an inner crater and an outer crater. It's hard to tell in this image, but the inner crater is parabolic, and this outer crater is a cone at the angle of repose of the soil. And it's a little bit easier to see it here. And that inner crater is constant size throughout the entire experiment, and the gas only interacts with the inner crater. This is a computer simulation. This is the gas velocity, and the right side is the gas pressure. So the gas is only interacting with the inner crater. And because the inner crater size stays constant for the entire experiment, it's a good experiment for getting data where you can collect data for a long time and the shape of the ground isn't changing. And so as I showed you, as I said, the outer crater continues growing. That cone keeps getting wider and wider and deeper. The inner crater stays constant throughout the entire test. Also, the depth of the crater. I plotted this against the logarithm of time, and that causes the depth of the crater to be a straight line. And so that means, just like the width of the crater, these are logarithmic. It's more easy to see it's logarithmic when you use a log scale here because it makes them straight lines. So we did these tests. A straight line only needs 2 parameters, a slope and an intercept. Turns out that the slope is... those 2 parameters can be written as a time scale and a length scale. And so those are the only two unknowns. What causes the time scale? What causes the length scale? We did lots of experiments varying the type of gas so that we changed the density, changing the velocity of the gas. That's what these different colors are. We've done experiments using different types of soil. So we have different density of the soil, different pipe diameters. And in each case, we would solve for the A and the B, the length scale and the time scale, and we would plot it as a function of the different physical parameters of the experiment. And what we found out, we also did this with different particle sizes. We did it with glass. I think that's aluminum oxide and corn. And we found different ways to get the data to collapse. We did reduced gravity experiments. Obviously, you get more erosion. The erosion is faster at low gravity. That was very obvious. But when you solve for the A and the B, if you had a fine powdery material, it would make this weird trend because at low gravity, it would fall off the trend line. When you used a more coarse material, the A and the B would follow the trend line. And so as a result, we, putting it all together, we came up with this equation. When you don't consider the powdery material, it's a little simpler. The numerator is the momentum flux of the gas into the experiment. The denominator is the potential energy required to lift the soil 1 grain diameter. And so it's the ratio. This could also be looked at as the kinetic energy density. But there was a constant out here, and the constant has to have the units of velocity. And we hypothesized that when the reason it falls off the trend for powdery material, there must be another energy in the denominator. This is a potential energy. This must be the cohesive energy of the soil because it's a powdery material. So that's where we stood about 10 years ago. I had a breakthrough just a few years ago. And so this is the latest result where I think we finally got an equation that predicts these effects. So again, we're trying to understand what's actually going on. If saltation is not the way that energy gets carried down to the soil, then what is the mechanism that energy gets carried? There was a theory by Leonard Roberts of NASA back in the 1950s to 1960s, and he just hypothesized without any empirical data that the erosion rate, the removal rate of mass of soil per area per unit time should be proportional to the shear stress of the gas. The proportionality constant has the units of velocity. And so he proposed that that velocity is the asymptotic velocity that the particles achieve after they've been lifted off the surface. So this left-hand side equals the momentum change in the soil. And the right-hand side is the shear stress in the gas, which has the same units, the same engineering unit. So this was a hypothesis. Problem number one is erosion is not really a shearing process, it's a lifting process. Problem number two is that particles don't achieve this velocity until downstream of where they got lifted. So how can something occurring downstream govern the rate that happened upstream? So we were skeptical of this theory. And so we did our own research, and we finally put together the final couple of missing pieces. So here's the clues. Clue number one is these stair steps. These stair steps are very mechanically weak. When we did these tests on the volcano, you could go back and smear your hands over it and they would just crumble and disappear. And then when you stirred up the ground and refired the rocket engine, it would make a crater with no stair steps. So it was exposing mechanical discontinuities that were extremely weak. And it was like the rocket exhaust was an archaeologist's brush, finally exposing little features in the ground, which would suggest that rocket erosion is actually a low energy process. How could it be a low energy process? Also, redeposition of dust in the same area that the rocket is digging the hole suggests that it's a low energy process. How could it be a low energy process? Well, an example of a high energy process is where you have this bed load transport, and the particles that are at the top of the bed load are in contact with higher velocity gas, and they're colliding and transmitting energy down to the soil. An example of a low energy process would be where the gas is in laminar flow and you get this stagnation of the gas between the grains down in that microtexture. That stagnation pressure is gently lifting particles up and out of the cavities. And then when they get exposed to the higher velocity gas, they get swept downfield. So we started to think, okay, so maybe the erosion is actually a very low energy process. The second clue was from these experiments. because the intercrater is constant, this tells us some things about the physics. It turns out that, I already said this, the erosion depth is, it varies with gravity and it's logarithmic. The inner crater is constant, whereas the outer crater keeps growing. It turns out that when you write the equations, you can prove that the erosion rate is increasing, but the erosion rate in the inner crater is constant throughout the entire experiment. And what's happening is that as your primary erosion is lifting soils out of the inner crater, then it's the crater gets too wide, and then the traction of the gas is insufficient to maintain this steep slope, and so it avalanches. And you get this avalanche dumping soil into the inner crater, which gets turned around and blown out as secondary erosion. And because the outer crater is getting larger and larger, the erosion rate is increasing proportional to the size of the outer crater, whereas the erosion rate in the inner crater is constant. What this tells us is that the removal or the changing momentum, taking momentum out of the gas, does not govern the erosion rate of the primary erosion. It's too much to really explain in a short lecture, but you can read the paper. I just want to say that with that insight, we were able to go back to these experiments, measure the width of the crater. We were able to write the width of the crater as a function of the stability of the soil on those slopes so that we could relate the width of the crater to the shear stress. And making substitutions, we could take the ratio of erosion rates at two different gravity levels. A lot of the different constants disappear. Everything in this equation turns out to be measurable, except for this D, the height that the sand has to be lifted, and this parameter, which we think is the cohesive energy density. So these are the two unknowns. We're hypothesizing this is cohesive energy density. We're hypothesizing that this is something on the order of a sand grain. So we can calculate the cohesive energy density using simple van der Waals forces, integrating over all the particle sizes in the soil. It turns out it's about 0.23 joules per cubic meter, extremely low energy. But that's what it is. And when you plug that in for alpha, and we've got our experimental erosion rate, the ratio of two different gravity levels, we know the crater widths at two different gravity levels for the inner crater, and we can solve for D, and it turns out D is equal to 1.5 coarse grain diameters. And so that partially validates our hypothesis. So it looks like this potential energy is an extremely tiny number, and the cohesive energy is also an extremely tiny number. So going back to the erosion rate equation, these are tiny energies in the denominator. This numerator must also be a tiny energy. All the energy is expended within the height of 1 grain diameter. And at that depth in the boundary layer, the gas flow is laminar. This is in the laminar sublayer of the gas. So the only other velocity that exists that could contribute is the molecular thermal velocity of the gas. So we believe U must be the molecular velocity of the gas. The molecular velocity times those other terms is the energy flux due to molecular diffusion. And so molecular diffusion of energy flux down in the laminar sublayer is a tiny energy flux. And so we think it's this tiny energy flux at the bottom of the boundary layer overcoming these tiny energies which governs the erosion rate. And so making those substitutions, we've got a final equation, and now we can test it. So I don't know how much time I've got left.
About 10 minutes.
Okay, plenty of time. So using the Apollo landing videos, we can see that the contrast of the dark and bright pixels is decreasing, and it's overall getting brighter as the dust starts increasing. And so looking at the histogram of pixel brightnesses, we can construct a metric that we can use to quantify the amount of optical density and therefore the amount of dust in each frame. And so writing the geometry equations, the sun travels down, it goes through this dust that's being blown, the rocket exhaust is blowing down, you're getting erosion at different points on the ground. We know the equations for the rocket exhaust, so we know how much energy flux there should be at each location. And so we can calculate the erosion rate, and we can assume that it fills this volume within 0 to 3 degrees angle. That's a crude assumption, but it's the best we can do. And so we can calculate the amount of optical density integrating along this path length down to the ground and back up again through the dust a second time to the angle of the camera. And unfortunately, we don't have good data on the Apollo cameras. They were film cameras, and we can't get the film any longer. The company no longer exists. So we can calibrate in the camera model. We can calibrate one of these two parameters just by looking at the brightness of the ground, but the other parameter we have to treat as an unknown that we have to solve in the curve fitting. And so we can write the optical density equations. We integrate over all the particle sizes. We integrate over the solar spectrum, over the width of the camera's response. These are the lunar mineral, the average scattering functions. We integrate over the path length. We integrate over all the points on the ground that's eroding, that contributes to that section of the path length, both for the downward path of the sunlight and then back up the upward path of the sunlight back up to the camera. And when you do the equations, it turns out that the optical density is dominated by the fraction of the lunar soil that's smaller than 10 microns. Unfortunately, we don't have good data on the fraction of lunar soil smaller than 10 microns. Turns out that this produces an uncertainty of about 50% in the results. So this is a way to get a lot of improvement, is get some data on the ultra fines fraction of the lunar soil. Also, the contribution of cohesion in the lunar soil is dominated by the particles finer than 10 microns. So it turns out that this tiny fraction of the mass of the soil completely dominates the erosion process. So when you fit it to the data, when you fit the theory to the optical density of the landing, the red curve is the theory, it actually gives us a really nice fit. Because there's two unknowns, let me go back. One unknown is this was the leftover constant. This is the erosion efficiency. What fraction of the diffusing energy contributes to lifting particles? I think it's a geometric term. It's another way to ask the question is what fraction of the gas in the stagnation layer is under the stagnation layer? What fraction of that gas is underneath erodible grains? The gas that's not under erodible grains is diffusing back up into the gas flow and leaving without doing any work. So this geometric term, I think we can solve that from first principles with a little more effort. But for now, we're treating this as a curve fitting parameter. And the other curve fitting parameter was the camera model, B2. And so with two parameters to fit, there is some degeneracy. But fortunately, there's only a narrow range of values of B2 that enable you to get a fit. So that results in about a 30% uncertainty in the results. So not bad to only have an 30% uncertainty. What this means is that the theory did predict the optical density of the blowing dust as the thing was landing. So the problem is, there was a problem in this. The first problem is that when you integrate this theory for the entire lunar landing, it predicts a much bigger crater than there actually was. What I left out is that when you're eroding the soil, you erode the loose layer first, and then you expose denser soil, and so it should reduce the erosion rate over time. And so we need a soil model. There's three sources of data. There's boot prints and wheel tracks. That data does not agree with the other sources of data. There's Lunar Source Book, which is based on returned cores and also cone penetrometry. Unfortunately, this model was anchored on soil that's 16 centimeters deep and deeper. And so if you use this all the way up to the surface, Z equals 0, you're extrapolating over the exact region that we care about. Then there's the Diviner thermal inertia data with Paul Hayne and coworkers. Fortunately, this curve is pretty good fit to this curve. They don't really disagree with each other. But we have an equation for the density of the soil with depth. We need an equation for the cohesive energy of the soil with depth. There's some experimental evidence that this is an exponential of the density, but we don't know what K is. So we've introduced a third fitting parameter in the model, and therefore we need another observable in order to do a reasonable job fitting it. What we need is an estimate of the depth of erosion. And we can get that by looking at these stair steps and counting them up and crudely estimating based on proportionally how much was removed from here versus from here, and therefore how much must have been removed here. And by doing that, you can crudely estimate that at the deepest point, 6 centimeters were removed. And so I ran multiple cases. I said, worst case, it was between 3 and 12 centimeters were removed. Turns out when you use 3 and 4 centimeters of crater depth, you cannot get the data to fit. But 5, 6, 12 centimeters, you can get good curve fits. So you can fit the erosion efficiency, you can fit the Kaminer parameter, you can fit this K parameter. Turns out almost all the uncertainty is due to this K parameter. How does the cohesive energy of soil increase as a function of its compaction? This could be studied in the laboratory. And so we could do a lot of work reducing these uncertainties. But the bottom line is this is the cumulative erosion as a function as the lander descends. As it descends, it's blowing more and more soil. And depending on that K value, it ends up blowing between 11 and 26 tons of soil during the landing. This would produce a crater of 4 to 5 centimeters deep. That would be a crater of 12 centimeters deep. The nominal case, 6 centimeters deep, means it blew about 15 tons of soil. It's a lot of soil that it blew. We're only making our measurement in this area until the lunar module's shadow got in the way. If we carefully cropped around it, we could only extend our measurements a little bit farther. After that, the cloud becomes opaque, and we need other types of instruments to verify the theory once the cloud is opaque. So this is what the crater looks like. This is exaggerated scale, but this is what it looks like without an exaggerated scale. There was no sharp peak in the center. We think the blowing off of that sharp peak was that big burst of dirt clods that happened right at the end, which caused it to be more leveled out right under the center line. Okay, so each Apollo landing blew 11 to 26 tons of soil. This was 4 to 10 times more than what we used to think. And that means the damage to the surrounding area is going to be 4 to 10 times worse than what we used to think. But there's huge uncertainty due to our lack of calibration of the fines content in lunar soil, due to the lack of our understanding of the cohesive energy of lunar soil, and because we didn't have calibrated cameras. And that last part is easily fixed. We just need to stick a landing on the moon with calibrated cameras. Firefly did it, and they got some great videos. I'm hoping that somebody's going to make those videos available soon. And we need lab measurements and more reduced gravity flights and lunar instruments. So because of this research, this was about 25 years of research, we finally convinced NASA that there is an issue here that needs to be studied. I used to spend all my time convincing NASA that it mattered. One time I gave a presentation to the head of NASA, and after my presentation was done, he looked at me and said, "Why are you doing this work?" That was Mike Griffin. And so I was like, Mike, that was my first sentence, was explaining it. But okay, we need multiple lunar payloads to measure the plume surface interactions, and they are being developed. We were able to produce a document, how to protect heritage sites on the moon. Congress passed a law to require compliance with that document. So the FAA is now on the hook to approve any lunar landings that they're going to not damage any Apollo sites with the plume surface interactions. The U.S. State Department and NASA have been developing the Artemis Accords. We can talk about that tomorrow. And the United Nations has been discussing it. But there's a lot more work that needs to be done. And we need to figure out ways to mitigate the blast, because when you're blowing 11 to 26 tons of soil with a 7.5 ton lander, how much soil are you going to be blowing with a Starship that weighs 150 tons? And so I think it's a pretty big issue. Okay, and there's a lot of fluid physics we haven't solved yet. I think eventually we need to have a facility on the moon to study the physics, because you can't really study it here on the Earth. All right, thank you so much for your attention.
Well, thank you, Phil. That's fascinating, all the practicalities that we don't understand for landing. I was wondering, the OSIRIS-REx blew, it's when it pulled away after collecting the sample, it blew this crater. And OSIRIS-APEX is thinking of doing something similar at Apophis. Have you thought about these super low gravity cases?
I was funded to support OSIRIS-REx. I've only been here to University of Arizona once before, and it was for an OREX meeting. And so I took these models we were developing. I was still an NASA employee at the time. And it turns out the mechanism in that case is diffused gas eruption. It blew this giant crater because the gas went down into the soil, and then the gas wanted to come back out. And there's very little gravity and very little cohesion in that gravelly material. So they gave me a soil model to use, but the soil model assumed there were a lot of fines. And so there was a lot less permeability. And I predicted it would blow a 1 meter crater. It blew like an 8 meter crater. And that's because it was a lot more permeable and a lot less cohesion than what the modeling predicted. And, to be off by a factor of 8, that's kind of the way it is if you don't have good data, because the models we're working with are extremely crude at this point.
Well, questions for Phil?
This is more of a comment, but speaking of the fines, the sub 10 micron grains, we had a whole survey node where this was a focus area. It was characterizing some of the properties of the sub 10 micron.
Was that Trex?
Trex, yeah.
Awesome.
So we've got a bunch of reflectance data and even optical constant data and samples. If some of those data might be of use to you.
Yeah, awesome. I did a literature review, and there were only 2 papers that tried to measure the submicron fraction of the soil. One was by Paul Greenberg, and the other was by Larry Taylor and coworkers. Park, the postdoc Park, was the first author. And the Greenberg data had an artifact. They had a dip in their curve. The dip happened to be right at the particle size between the 2 different measurement instruments. So everybody thought it was an artifact, and then it was. The other data by Larry Taylor, they used a method that avoided the artifact, but unfortunately, they only measured particles finer than 10 microns, and they didn't report what fraction of their soil was that fraction. And so we had no way to concatenate their data set to the rest of the lunar soil. And so what I did in this research was I said, well, I extrapolated from the curve of the lunar source book, and I said, well, the extrapolation is pretty bad. It looks like it could be anywhere from 3% to 20%. I bounded the problem with these numbers. And then I solved the problem using all these different cases. And that's where you get like a 50% variation in the result. So it's just because we don't have a good data set to say what fraction of the soil is submicron fines. Yeah.
Other questions? Yeah.
I don't understand this brightening mechanism. Where do the fines come from?
Yeah. So what I think was happening, now this is just speculating, or hypothesizing, what I think happened on Mauna Kea is that the fines were all mixed in with the tephra, because you could grab it and throw it and it would release dust when you threw it, So there was a lot of fines, and the fines tended to be yellower than the other soil, just because I think the minerals that broke to the finer size were a yellower mineral. I don't know the details, but some geologists who were there convinced me of that at the time. So what happens is the fines are being released as it's digging the hole. It's digging non-homogeneously around the rocks and everything, and it's releasing particles, fine particles, and then it relies on gas dynamics to lift the particles up into the higher velocity gas and carry them away. And apparently the fine particles are having a lot less lift force. And so they're not being lifted as high, and so they're more likely to settle back down again. So you're constantly eroding and constantly settling. And so where they're settling is moving around during the process, but there's always ends up being a concentration left over because of that process.
So just an observation, when you fire on Earth parallel to the ground, the opposite happens. The dirt is absolutely scrubbed clean. All the dust is gone, and only the larger particles remain in the zone near. So I don't understand the behavior, but it's different.
Well, one difference is like in these lunar cases, the gas was sufficient to remove all size particles. But if you do a test where it's not sufficient to remove all size particles, you will end up building up a armor layer of coarser ones. So that's another complicating factor.
I've got a couple of questions online. Veronica Durfee asks, do you know if the 10-centimeter rocks blown by the Apollo landing produced craters that were also imaged by the landing cameras? Do we have measurements of these little craters? If so, how do they compare to your Mauna Kea experiment?
That's a great question. And no, we didn't look into that. Yeah, so there should have been some secondary impacts from those ejecta hitting the ground. During the recent Firefly landing, you could see the dust going out over the horizon and then the sky clearing to black as it goes down over the horizon. And then near the end, you see this one rock fly off and then land. So there was one very prominent rock that got blown out near the end of that video. So in the future, that could be a good thing, drive out to where it impacted and study the secondary impact physics.
And maybe the last question from Jacob Bernal is, would you expect the lunar dust to exhibit any interesting electrostatic properties? Would that attraction influence the initial crater formation?
Great question. Yes. I never did come back and explain something. I mentioned during the video, it took about 20 seconds for the haziness to clear the air, clear the vacuum. It took way too long to clear. It should have cleared in 2 or 3 seconds. We did calculations on the ballistics. It should have cleared in 2 to 3 seconds. We don't know why the dust was still hazy, but you can measure it. It exponentially decays over the time constant of about 20 seconds. And so there's a couple of theories. Theory number one is that there's gas in the soil and the gas is coming out and lofting more dust. I don't really think that's a viable hypothesis. The other one is that it's electrostatics, because we do know rocket exhaust is positively charged in the usual case. It's hot enough that it's ionized. It's a plasma. And so there's a container effect in the rocket nozzle because electrons are smaller than nuclei. They tend to get absorbed into the container more often than the nuclei do. And so in general, it's called the container effect. In plasma physics, the boundary around a container will be a positively charged piece of air. And so this is exiting the nozzle with this sheath of positively charged gas surrounding the neutral gas. And people, there've been 1 or 2 papers back in the 60s, Aronowitz and Sabaroff were the 2 authors that measured this, and they measured the positive current of different rocket nozzles. Years ago, we were set up to measure this. We were going to fire a rocket nozzle at the Johnson Space Center. I asked this young woman to go out with the equipment. She was going to run the test. They were going to, they had a Faraday cup with the bottom cut out. We were going to put around the rocket nozzle to measure the increase in charge as the engine turned on and then it's dropped back down as it goes off. And she had an electrostatic charge sensor to measure the residual charge, if there was any, on the box of simulant. But the morning she was supposed to travel, NASA called us up and said, don't bother coming. Last night we were doing a test and our rocket test stand disassembled itself. So they blew up the rocket. And so that was the closest we ever came to getting those kind of measurements. I think it's important to understand, if you're perturbing the plasma environment around your spacecraft and you're going to make measurements in that vicinity, you should understand the environment. So I think it's a pretty important question, but there's never been any work to try to figure it out.
Oh. Well, I'm just reflecting that I guess this all started with Buzz Aldrin saying, kicking up some dust in the Apollo 11 landing audio. So thanks very much, Phil. Really appreciate it. Thank him again.
Can I just, since you brought up Neil Armstrong, I got to share this story. When I submitted this big paper back in 2011 to JGR Planets, the peer review came back and one of the peer reviewers identified himself as Jack Schmidt. and there was one, when I was talking about the haziness tapering off, his comment was, Well, I didn't see that when I was on the moon. And as a researcher, I didn't know how to reply to that comment, but he let it get published anyways.
Yeah, it's nice. There's still some people around that were there to see it. So
Yeah.
all right, let's thank Phil again.